Hello, my name is Alejandro and I'm a PhD student from the Peking University. Today I'm talking about exciting modes of gravitational waves due to a motion of the source, measurability for extreme mass ratio inspirals. This presentation is based on these two papers, which I have published with my supervisors, Xian Chen and Paulo Seoane, and some other collaborators like Alvin Chua. One important thing to know about extreme mass ratio spirals, which also applies to gravitational wave sources in general, is that they are usually hosted in some system. These systems are very often galaxies. And one important thing about these galaxies is that they are very often, roughly 60% of them, organized in so-called galaxy clusters, containing dozens to hundreds of galaxies. So these galaxy clusters have a very deep potential, which induce a motion to all the component galaxies. This has been measured for light, which we show in this plot. And here we can see that for each galaxy cluster, so each point represents a combination of thousands to hundreds of galaxies, have a velocity dispersion of around 1000 kilometers per second. Now, because all these galaxies moving inside these clusters are not perfectly tuned with the Earth, this means we are also seeing these galaxies to be moving with a velocity of around 1000 kilometers per second. So why is this important? Why do we care about the velocity? Okay, let's first consider the typical picture or the standard picture, which is usually considering gravitational waves as plane waves. In that case, when you have the velocity, the only effect you have is a Doppler shift, and then you have the so-called mass redshift degeneracy, which was a result from Werner Schutz's seminal paper from 1986, where he basically showed when you have a source which is redshifted or blue shifted, it looks the same as a source which is not being blue or red shifted, so it's not moving, for example, but have just a different mass scale. However, strictly speaking, gravitational waves are not plane waves. This is because they contain several modes which are related to their spherical properties. And now, let's look here on this radiation pattern. On the left side, we have the radiation pattern for the plus polarization, and on the right side for the cross polarization. For a source at rest, we see that the emission is quite regular. There's almost no anisotropy, except a little one, which is because this is a source of unequal mass black holes. However, when the source is moving, which I show in the lower plot, we see that there is suddenly a stronger anisotropy, for example, a much stronger emission close to the direction of the angular momentum of the binary. And that, for example, for the cross polarization, this line where you have no emission of cross polarization basically disappears here. So, and why is this important for the modes? This is because the modes of gravitational waves are basically computed taking a combination of the plus and cross polarization and decomposing it using the so-called spin to spherical harmonics. The spin to spherical harmonics are a basis of shapes, you could say. Actually, they are functions, but like of shapes, which you can use to decompose spherical properties of different objects like gravitational waves. And here we can see for different harmonics they have different shapes. For example, when the source is very regular, which is very isotropic and described by almost a sphere, only the two modes are quite good to describe the emission of the source. However, when the source becomes distorted, you need some other spherical harmonics, some other of these shapes to describe the radiation pattern. So when the radiation pattern changes, this means you have indeed different modes in your gravitational waves. In one of the papers, I have computed how the modes of a source which is moving looks as terms of the modes of the same source at rest, which is the HLM, plus some correction which is proportional to the velocity, and again some combination of the original modes times some coefficients which are also dependent on the mode you are considering. And why is this important? This is because the gravitational waves that we are detecting are not just one of these modes, it's not just a dominant mode, but a combination of them, so it's a superposition. Therefore, when their relative strength change, their superposition also looks different. Here we show for the same source we presented in the previous slide, considering one particular ray, how the gravitational waveform look for this ray for the plus and the cross polarization for a non-moving source in red and for a moving source in blue. And as we can see, the emission looks slightly different. For example, in this case, the plus polarization of the moving source is a bit stronger and the cross polarization is much weaker. Moreover, we see that there is a difference in the phase, which is particularly interesting because it's a time-dependent difference in the phase. Here, I should mention that we have chosen these sources in a way that when you would be considering only the 2-2 mode, these waveforms would look exactly the same. So we have corrected for the difference in the mass due to the redshift, and we also are considering the rays that they are the same in the source frame. So only having the 2 mode, you will have no difference, but considering the additional modes and the change of the relative strength, you have now a difference in your gravitational waves, which is, as I mentioned, time dependent. This is interesting or important because when you have a time dependent difference, in particular a phase shift, you will have a mismatch between these two kinds of waveforms when you try to detect such a source. We have computed the mismatch again for a source, now for extreme acceleration inspirals. The previous one was for the merger because it's easier to visualize, but now for extreme acceleration spiral, which is inspiring around 2 years until short before plunge. And we have computed the mismatch between a source which is not moving and the same source which is moving with a velocity of around 1000 kilometers per second. Again, correcting for the mass redshift so that it would look like the same when only considering the 2-2 mode. And here we see that there is a quite significant mismatch, in particular when we are close to seeing the source from edge on. We also computed which signal to noise ratio would be required to detect this mismatch, and we find that when you are really close to edge on, around 20 for the SNR would be enough to detect the source, so you don't need particular strength sources. And when you go to SNRs of up to around 100, we would be able to detect this difference for inclinations from around 70 degree to 130 degree, so for around 1/3 of the possible inclinations to see. We then also considered how accurate the velocity could be detected for this example, and also which effect this would have on the masses. We see that for this case of a source moving 1000 kilometers per second, we would be able to measure the velocity to a level of around 40 kilometers per second based on a Fisher matrix analysis. So this is a quite idealistic assumption, but even if you say, okay, for more realistic detection, the velocities are going to be weaker, maybe for 100 kilometers per second, we could say we're going to be able to detect the velocity, which is around a 10% level, which I think is very good and quite accurate for the detection of motion. When we look on the impact of the motion on the detected masses, we see that there is not much difference in the detected masses for the primary and the secondary black hole, for a moving source and for a source at rest. However, these are the masses of the source seen in the observer's frame. But as I mentioned, these sources are being redshifted, so the moving source, actually the original mass, is lower by a factor of, for a velocity of 1000 kilometers per second, around 10 to the 3 of the relative mass that we are seeing. So actually, if you are measuring these masses, but you are not considering the velocity, the bias or the error that you are causing in the detection of the masses is not of the order which is showing here, which corresponds to an order of around 10 to the minus 69. It's of 10 to the minus 3, so the error is 3 orders bigger than expected. So therefore, it is very important to really measure the velocity so also can extract that information of the EMRI accurately. So to summarize again my results, sources are usually in host galaxies which are moving with velocities of around 1000 kilometers per second relative to us. When the source is moving due to a center of mass motion, we have some excitation of additional gravitational wave modes, which can be used to break the mass redshift degeneracy, and which we also can use to detect the velocity of the gravitational wave sources and their hosts, which additionally will allow us to retrieve the information about the source more accurately. So, thank you very much for your attention. Here is the literature I used in my presentation, and if you liked it, I would like to recommend you these 2 papers where I derived the theory and where we show how the measurability is for extreme acceleration spirals. Thank you very much.